What up, everyone? This is LeetCode 108, convert sorted array to binary search tree. So we have a sorted list as our input, right? Um, it's just an integer array nums, and it's sorted, and it's an array. So we have to take this array that's sorted, and we have to convert it to a binary search tree that is height balanced. Now, if you'll notice here, in the middle element in the list, that's our root node, right, for our tree when we construct it, and everything to the left is in the left subtree, and everything to the right from that middle element is in the right subtree. Now, even if you didn't have this picture and you were just given this, you were just given an input like this, we would kind of intuitively know that we still would have to do something like this because we would have to get the middle element, right? Um, and that would be our root node. We intuitively we would still kind of understand that because we have to make sure that the binary search tree is height balanced, right? So we need we need to pick a root node such that roughly around half of the elements are on the left side and half of the elements are on the right side, right? When we construct our binary search tree, okay? So let's think about how we're gonna do this. Okay, we're gonna get the middle element. Okay, so we're gonna create a function, right, to handle this because we're gonna have to do this recursively. Okay, so we're gonna have to basically, in order to get the middle element, right, we would have to do something like a binary search, right, to kind of get the middle element. So, right, there's plenty of problems with binary search if you haven't done that. But to get the middle element, right, we would do something like left plus right divided by 2. Okay, that's how we get the middle element. And so we get the middle element. Okay, that's our root. Now let's handle everything on the left, right? How do we get this 3 or this 10, right? Well, we can just do binary search again on everything to the left of this, right? So we have these elements. Let's do a binary search, right? If we do a binary search like this, left plus right divided by 2, we'd actually get a negative 10, which is also an acceptable answer, right? Um, then we could do and then we could now, when we're at this 10, if we go left, there's not going to be anything, so we wouldn't do anything. Now, when we go right, we actually have this 3 left. So when we do a binary search, we get this as our midpoint, and we add this as a node. Okay, we handled everything to the left of this middle element 0, and and then we would do the same for the right, and we would get 5. Nothing to the left of 5, but there is that 9 left, right? So let's handle that 9, etc. Okay, so that's how we do that. So we do need kind of like a left and a right pointer in order to calculate our midpoint, right? And right, we're just kind of making like a template, right? Or template, depending on how you pronounce it. Uh, so we're gonna call this function right down here. We're gonna pass it the 0th index and then the last index, which would be length of nums minus 1. Okay. Okay, this is our template so far. Okay. So initially we're passing it the 0th index, which would be this, and then the last index, which would be this. And we're going to use that to calculate the midpoint, right? So we should get, this mid should be 0, okay? So now we're gonna set this midpoint as a root. So we're gonna say root is equal to tree node, and we're gonna say nums at mid. Again, this mid really is obviously an index, right? That's why left is 0 and right is length of nums minus 1, right? So when we calculate this mid is not the actual element, but it's just the index. That's why we do nums mid right here. Okay, so so we're setting 0 as a root node. Okay, so now let's do root.left, right? And we have to call this recursively, right? Because we need to handle every element to the left of the 0. So we're gonna do something like this. Okay. Now, and also we have to make sure we do the right after a recursive, handle every number to the right of this midpoint recursively. So we're going to say this. Okay. Now this construct part here, right? What is going to be our parameters here, okay? So here we're at 0, right? Now, when we handle everything to the left, what are we setting here, right? So the left is already at 0, right? So we probably don't want to move the left pointer when we're handling everything to the left of the 0. We're going to have to move the right pointer, right, which isn't right here. It's at the last element, right? It's pointing at the last index, I mean. So we would probably do what? This is our midpoint. So if we want to handle these numbers, we'd probably do what? We'd probably set the right pointer at midpoint -1, right? So the left pointer would be here and the right pointer would be here, and we would handle that. Okay, so the left pointer, we're just going to leave it, and the right pointer, we're going to do mid -1. Okay, now let's say we handle all of that, right? What about when we handle everything to the right of the 0, okay? Well, the right pointer is right here, so you probably don't want to move the right pointer, right? If it's pointing at the last index. So we would probably just want to do what? This is the midpoint, so we probably want to do midpoint +1 and keep the right pointer where it is, right? So the left pointer would just be mid +1. The right pointer would be just right. Okay? Now when we're done with that, we just return the root. Okay? Now I'll go through an example just to show you. Maximum recursion. Oh, right. We need a base case. Since we're doing recursion, we need a base case. So we're going to say if left is greater than right, then just return none, right? Because let's say we're at this midpoint 0, right? And we're going and we're handling everything to the left, right? So our left pointer is at 10. We move the right pointer to this 3. When we calculate the midpoint, it would be 0. So we do this 10, right? This is what this algorithm really was going to produce this picture, not this one, right? I mean, you can produce this picture if you approach the problem differently, but for this, this is also an acceptable picture, which is what our algorithm is constructing. So we're going to have this 10, right? So if we're at this 10, right? Well, we need to make sure there's nothing to the left. So when we check to the left, we're going to set the right pointer to the left of where the left one is, right? The right pointer is going to be here, but the left pointer is here. That's why we need a base case, so we don't continually keep, doing recursion when we don't need to, which would kind of put us in an infinite loop. So, yeah, this code isn't too complicated, but so we do this 10, right? Okay, we go root.left, and we'd hit the base case. When we're at this -10, right? Okay, let's go to the right. So we would do mid +1. Mid is 0, right? So 0 +1 is 1. And again, when we go here to this 10, the right's already set to 1. And left is set to 0. So we calculate the midpoint, we're going to get 0. That's why you do this 10. So 0 + 1. So our left would be at 1, our right would be at 1. And this would be the midpoint, and we would handle this. Okay, then we would just get out basically nothing to the right anymore, right? We would, because our left pointer would go beyond the right at this point, so we'd hit a base case and return to the 0. Okay, and then we handle everything to the right. So I hope that makes sense. I'll just do this, right, just so I can show you. So let's just print this. All right, I'm just gonna print this just so I can show you, see if it makes a little bit more sense. Up here, let's just print the... I actually don't want to do that. Let me put this up here. Right before we do any recursive calls. Okay, so we hit this 0, right? Then we go to this 10, right? And then we go to this 3, and then this 5, and this 9, and this 9. Okay. Yeah, 0, -10, -3, and then 5, 9. So I'm just showing you kind of where our pointers are pointing at in each of the processes. Okay, And here's a example 2, which is much simpler. So yeah, I hope that helps. And I'll see you in the next one.